Welcome to The Foundry by Forge College. Today's explainer is all about conquering the final dragon of the Bitcoin fundamentals track, your capstone final submission. You know, you've spent the last few modules building some incredibly complex things with SegWit and Taproot, but today we aren't just coding, we're putting on our master chef hats. We're going to take all those raw ingredients and plate a flawless Michelin star meal.
So let me ask you a question. You built the code. It runs perfectly on your laptop. But can anyone else actually run it? If you hand your recipe to another chef, can they bake your exact cake in their kitchen, or is the whole thing just going to burst into flames? That right there is the critical problem of reproducibility. And it's the exact problem you have to solve in this final submission.
Okay, let's dive into this. Think of our agenda as a comforting kitchen prep list. First up, the final challenge. Then, assembling artifacts. From there, we'll unpack the power of reproducibility, crafting the deck, and finally, the final checkpoint. All right, Section 1, the final capstone challenge, plating the perfect dish. So, you've already done the heavy lifting with your transaction demos and your privacy analysis. Now, we have to bundle all of that into a reproducible artifact. What does that mean? Well, it's a packaged bundle of your code, your raw data, and instructions that allows absolutely anyone to perfectly recreate your exact results. If you want the instructor to verify your cake tastes good, you can't just hand them a picture of it, right? You have to give them the raw ingredients and the precise oven settings. Moving on to Section 2, assembling your artifacts, gathering the ingredients. Think of this required folder structure like setting up highly organized prep stations in a professional kitchen. You've got your paper folder for the main menu, then your artifacts folder, which is neatly broken down to TX demos for your transaction hexes, analysis scripts for your code, and raw data for your CSVs. You'll want to keep your README and your changelog right at the root, and finally, your slides folder. Keeping everything in these exact stations means the verifier can find exactly what they need instantly. Now, what's really interesting about this grading rubric is how clearly it maps exactly what the instructor wants to exactly where it lives. Your argument, which needs a clear thesis and 3 threads, well, that lives in paper sections 1 through 3. Reproducibility, that needs a one-command script right at the archive root. Evidence must cite artifacts inline or in the appendix. The presentation needs to be under the time limit within the slide deck itself. And peer feedback is documented right there in the supplementary changelog. It's basically your ultimate foolproof checklist for passing.
Let's look at how you actually write these claims in your paper. On one side, we have a vague statement, Taproot saves space. I mean, sure, that sounds nice, but where is the proof? On the other side, we have the gold standard, Taproot saves space as proven in artifacts/txdemos/taprootdemo.xtt. Your menu description must directly reference the exact ingredients you used. Evaluators need to reproduce your path from the claim straight to the evidence without any friction whatsoever.
Which brings us to Section 3, the power of reproducibility, the perfect recipe.
This is your biggest technical hurdle, honestly. We have to avoid that dreaded developer excuse. Well, it works on my machine. Enter reproduce.sh. This is the magic one-command script that absolutely must live at the root of your folder. Think of it as an automated master chef. The instructor just presses one button, and this script perfectly executes your instructions, exits with a status 0, and writes a neat little reproduce.log. It proves your work isn't just theoretical, it is fully operational.
So, how do we actually bulletproof our code? First, that one-command reproduction we just talked about. Second, include the raw CSV inputs and the parsed JSON witness data so evaluators can cross-check without manually recreating transactions. And finally, if you have complex environment needs, just use containerization like Docker. Look, we've all been there. You forget to mention one random pip package and the whole thing crashes. Docker acts as a standardized, foolproof kitchen. Actually, scratch that. It's more like a completely self-contained restaurant. This focus on robust, verifiable environments is a huge part of the learning philosophy in Forge College programs. You're not just writing code here, you're engineering professional, verifiable deliverables. Let's move to Section 4, crafting the presentation deck, plating the meal. You've done the science, and now you must communicate it clearly. And this brilliantly illustrates your strict budget for the presentation, which is limited to 10 to 12 slides total. You need 1 slide for the problem statement, 2 to 3 slides for your technical evidence block, 1 slide summarizing the reproducibility steps, and a closing Q&A slide with your artifact links. No fluff, just the absolute meat of the research. Keep the golden rule of 3 in mind throughout this entire process. You need 3 core findings in your deck.
Your paper must show at least 3 argument threads. And during your presentation rehearsal, you need to practice answering 3 likely Q&A questions. 1 on a transaction example, 1 on your measurement methodology, and 1 on privacy limits. 3 is definitely your lucky number.
All right, Section 5, the final checkpoint, the taste test.
Let's move on and see how this builds. To completely eliminate your submission anxiety, you're going to run through this binary self-verification sequence. Step 1, paper sanity check. Does your thesis appear early and are artifacts referenced correctly? Step 2, run that reproduce.shay script and make absolutely sure it exits 0. Step 3, check your artifact integrity. Make sure your hexes and parsed JSONs actually match. Step 4, rerun a measurement script and verify the numbers match your paper. And Step 5, a timed presentation dry run. If any of these fail, just fix it, document it, and run it again.
Once every single test in that checkpoint sequence passes, there's one final, crucial step if you're using a Git repository. Tag your final commit as v1.0-submission. This effectively seals the completed dish for delivery. It tells the grader, hey, this is the exact verified version. And finally, Section 6, the bill, conclusion, and next steps. You should be incredibly proud of packaging these complex concepts into a verifiable deliverable. So, what's next? Well, first, schedule your presentation slot. Then, you're going to pivot. You'll start preparing for the next module by reading about Ethereum core components and roles. Get ready to take all this deep Bitcoin knowledge you just mastered and contrast it with Ethereum's completely different core architecture. It is a fascinating shift for sure. I want to leave you with this final thought. Verifiable research isn't just about passing a grade, it's the foundational ethos of the entire blockchain. Think about it. Trustless verification is the literal point of Web 3. By building reproducible artifacts, you aren't just doing homework, you are embodying the philosophy of the technology itself. So what verifiable reality are you going to build next? Head over to forge.college to continue your journey and explore more amazing Web 3 topics. Thanks for letting me guide you through this explainer today.